So today we're talking about convection currents, okay? And they are crazy. So if you ever wondered why, if you are standing next to a fire, it's so hot right next to the fire, and then so hot on the top, you know, like a candle as well. You can't put your hand on the top, but you can, it's much less warm next to it. Why is that? What about a pot of boiling water? How is it that you're just putting heat on the bottom, right, on the burner, but it's heating the entire pan of water? There's a huge temperature difference there. And then once it gets hotter and hotter, it starts rolling and then it starts boiling. It's all convection. So before we can get too deep into convection, I need to tell you about what drives convection, and that's density. So convection is the movement of water driven by changes in density that are caused by temperature changes, okay? So it's a big concept. This class meets a lot of middle school science standards, and some of you adults will probably learn something as well. So I want to show you, just briefly remind you about density. So a lot of people think density has to do with how heavy something is, and that is not always true. So if you look at the slides over here, one of these is more dense, the most dense. Density is simply how tightly packed the molecules are. So in this case, we're mostly talking about water, okay? So colder water is more dense. It has less energy. The molecules are tightly packed together, like in example B. As the water heats up, it expands. That kinetic energy that goes in to heat the water causes the molecules to move faster and get further apart. So that is, you would see in slide A, is a little bit less dense, warmer water. Slide C, even less dense. And then D, very less dense. And in our case, that would indicate warmer water. So in water and in many other substances, there's changes in density associated with temperature. So we're going to do a demo here. And now that I've realized the sound is on, we'll go back to our jar. Okay. See if I can get this level. All right. Okay. I'm coming. Okay. Hi. You don't really want to see me anyway. All right. So here we have just a jar, regular jar, nothing in it. So the pressure from the air on the outside is the same as the pressure from the air on the inside. So we're going to use air for this because it has changes in density as well, expressed in changes in pressure. Okay, so what I have here is a balloon filled with water. I'm going to put my safety goggles on just to be, you know, extra safe here. Okay, so balloon. Clearly, I cannot get this balloon to go into the jar, okay? I'm trying, even though it's a water balloon, I can't really squish it and make it go in there, okay? So, I'm going to use science. Let me aim this up just a little bit so you guys can see me. Okay. Science. Okay, so this is a piece of paper, okay? These are matches. I should mention the museum's closed. I'm the only one here. There's nobody around in the fast waterway seaport. So I'm very, we'll see what happens with this. Hopefully there's not too much smoke. I'll probably run it outside at the end. So what we're gonna do is, we're gonna light this piece of paper, okay? We're gonna drop it in the jar. We're gonna put the water balloon on top. Now, hopefully the whole thing doesn't explode. But what should happen is you'll see the balloon bounce like this as the air inside the jar heats up, okay? And then it expands like we talked about. It becomes less dense and it starts coming out the top, right? So the air is getting hotter and expanding. And as it's whooshing out the top of the jar, the balloon shakes. Now, when enough air is out of the jar, the balloon will seal itself onto the top of the jar. And then things are going to be less dense in here with less pressure than what's outside. And hopefully the balloon will get sucked into the jar and not pop. I don't know. Anything could happen. Let's give it a try. Step 1, learn how to light a match. There's the wiggling, and there it goes. Ah! All right, so as you can see, I didn't drop the paper completely right side up. So, but now I can't get it out. So it's pulled the balloon about halfway into the jar because I'm bad at fire and my paper fell over, so it didn't burn all the way. So what we'll do is we'll get it out, try it again, see if we can get it to suck it all the way in. Just, why not? So in order to get it out, I need to create more pressure inside the jar. It's stuck, okay? I cannot get it out. So I need to take more air molecules and put them in there to raise the density of what's in the jar. So this could be bad. Or I might just pop the balloon. Let's find out. Okay, you can see that release there. Okay. Oh, we got to get deeper in. Hold on. Here we go. Science! So fun. All right, let's try this again. See if I can't do my paper better and get it to stuff all the way in. Now, kids, if you want to try this at home, you absolutely need to have an adult present, okay? You need to wear safety goggles, and I recommend that you use a glass bottle so that it doesn't melt. I tried this with some water balloons, and I bet you can guess how that ended. They exploded. So you just want to use a regular balloon. You put it over the faucet, put a little water in it, okay? Let's try this again. Here it goes. And I can help it out a little bit as it gets hotter. And we got a little bit further that time, all right? So that is really fun to try at home. See if you can get your balloon to go all the way in. So now it's time to talk about convection currents themselves. So I'm gonna come back over here. Turn back on my screen share so that I can show you guys a little bit about convection currents. Okay. So remember, the reason why that happened is the air outside is more dense. Okay, it looks like it's sucking the balloon in. It's actually pushing it in, okay? Because the air inside is less dense. All right. Okay, so this is a very, very busy graphic, but it's talking about showing you the difference in density in a pot of boiling water. So at the bottom of the pot of boiling water, where it's heating, okay, in the beginning at least, it's less dense, right? And then, what do we know about warm air and warm water? It does the same thing, okay? It rises, it goes up. So what happens is, you're boiling the water, that heavy, cold, dense water at the bottom of the pot. It rises up to the top, and as it rises, as it warms, it rises and becomes less dense. Then it gets to the top of the pot where the cold air is, okay? It starts to cool down, sinks back down on the sides, becomes more dense again, and the whole thing goes over, and that's what boiling is, okay? Now, I am going to show you what that looks like in real life in just a second. So here is an illustration. That's a flame there at the bottom, and here you can see the circulation going around and around and around. That, my friends, is convection. That is a convection current. So what we're going to do now is another experiment that you can replicate at home. And this is kind of an example of what happens in the ocean. So the ocean, I'll stop my share here, is a very big place. Okay, and as we know, in the ocean, we have, in the world, there's cold parts of the world, right? Like at the poles, very cold there. And then in the center, around the equator, it's warmer. So I'll post some more information about this. It is kind of a higher level science, exactly how this convection works. But basically, cold water starts in one area, travels deeply along the seafloor. It follows some certain submarine under the water valleys until it gets to a warmer spot, and then it gets warm up to the surface, a shallower part of the ocean, travels around warm on the surface for a while until it gets back to one of those cold spots and sinks. So this conveyor belt, we call it, goes all the way around, not like around the world in a circle, but it makes a loop through the oceans and through these dark spots and warm spots. It is one of the large contributors to weather and what happens in our atmosphere. And the estimates are it takes about 1,000 to 1,600 years for a single molecule of water to make that entire journey all the way through the oceans and around the world. So we're gonna make the journey right now over here in a little demo. I'm just gonna check real quick, see if we have any questions. I don't see any yet. Okay. All right. Demo time. So in order to do this demo, you're going to need a couple of things. You're going to need hot water, which I've been heating up from my kettle over here, some ice, and these are listed online. You're going to need food coloring. I like to use red and blue. And then you're going to need something to go underneath. One can be empty, and then one mug to put your hot water in. So I'm going to go get my hot water and my ice, and I'll be right back. So I like to use an ice pack like this, like you might have in your lunch. But you can also just fill a water bottle like this and put it in the freezer overnight, or anything else. A Ziploc bag will work, but it's good to have a good block of ice to really get this going, okay? And I'm just heating up my water again because we want it to be as hot as possible. So I'm gonna get that in 1 second. Okay, so I have my kettle with hot water. That right there. Okay. Now this is just a regular bin full of water. And we're going to balance that right here like this. So first of all, we're going to take our red food coloring, put it right here. And you start to see right away that the food coloring is going to show us our currents, okay? That is going to start to rise, powered by the hot water coming from the mug. And then on this side, we're going to put blue food coloring, and we're going to put our ice over here. Now, remember I said in the ocean, This takes 1,600 years, right? 1,600 years. So hopefully it's slightly faster here, but we are gonna have to be patient. So while this is getting going, I'm gonna position the camera a little bit closer so that you can see a little bit better. Okay, so what we have starting to happen here is we have our red, warm, less dense water rising. Now, when water rises, it doesn't just leave a hole. Something has to come in to fill its place. And that's the basis of convection currents. So this water, as it's really going now, is less dense, okay? Move out. Is that easier to see? Use my lab coat here. Make it worse or better on the camera? No, it's better if I'm not in front of it. Okay, so I'll go over here. So as the warm water is rising, you can see the warm water is rising, it's less dense, but it's not just going up, it's traveling across the container, okay? And the cold, dense water on the bottom is creeping along the bottom here over towards the warm water. So this is less dense, okay? It gets up to the top, doesn't have anywhere to go. It's getting cooler and cooler as it moves away. And then as it gets closer to the ice, it gets heavy again and it's gonna start to sink. I feel like that part's pretty intuitive. The part that's really weird is how this blue, to me, is stretching along the bottom. And the reason why that cold, dense water is doing that is because it's trying to fill the gap from the rising warm water. Now, in the ocean, it sort of works the other way around. It's the cold water driving it. In our demonstration, it doesn't really matter what starts the circulation as long as you can see that it's happening. So I'm gonna try to move the camera even a little bit closer so you can see. It's easier to see maybe from the top. You can see that blue water, cold, dense water is basically scraping along the bottom of that container, taking up, it's being drawn in by that rising warm water. Because the warm water is rising, again, something has to come in to fill its place. And the same thing here. The cold water is sinking, something has to come in to fill this place. So the red water is being drawn over, being cooled by the ice. And pretty soon, this is just gonna be one big purple mess. This is really fun to do over and over again if you're a giant nerd, like obviously I am, or maybe you just like science and you want to explain convection to your friends. It's very, very simple to do. So eventually, this red water is going to get cold, and it looks like it's just starting to do it now, and sink. Now it doesn't change color, right? Because the dye is the same color, but you can see the red water making it all the way around. Now, as the water in this container here equalizes, the convection will stop. Now, some people talk about climate change, and when they talk about the problem with the fact that our poles are getting cooler and that it's slowing down the ocean currents, this is what they're talking about. So you can see even now the ice isn't as cold and the warm water isn't as warm and things aren't moving as quickly. So nobody really knows for sure how that will affect weather. But if you delve deeper into this subject, you can learn a lot about convection currents and weather. Now, this doesn't just happen in the ocean, right? It also happens in the water, in the atmosphere, right? It's one of the ways that we make weather. That's why when you go to the beach, there's always a nice breeze. And that is because the land and water are different temperatures. So again, it creates a convection current. When you have two different temperatures and something moving in between them like air or water, the changes in density can create a really rapid movement, like wind if it's in air, or current if it is in water. So we are almost finished up here. Okay, so moving on. Here again is that graphic just to remind you of how this works. Okay. And then I wanted to show you this. It's a little bit hard to see, but this is an example of convection happening inside the Earth's crust. It also has to do with plate tectonic movements. So convection is everywhere. It's a really important concept for everybody to understand. So that is all I have for you this morning. If you have any questions, you can type them here, or I'll be posting this video on YouTube and Facebook, so we'll check back later. And I hope that you get the chance to try some of this at home. Have a wonderful day.